Okay. Today we have Joseph to tell us about singular points on Positroid varieties and its applications.
Awesome. Yeah, thanks for having me. Excited to be giving the seminar talk. I have 80 slides, but some of these I'm just going to skip over. So the outline is this. I'll be talking about some background related to the Grassmannian slides I'll skip over. I assume everybody sort of knows that. And I'll quickly go over Positroids and Positroid varieties. I'll take a slightly different, maybe slightly more combinatorial perspective than Daoji gave last week. But since you heard something about that last week, I think I can maybe not spend too much time. I'll then start talking about some other combinatorial machinery that will be necessary for understanding these main theorems that I'll present. I'll talk about this partial order that you can put on this set. Then I'll end with something about physics that I was thinking about. So the setting is the Grassmannian. It's going to be the complex. Well, messing up. It'll just be ORC. And I guess examples. I'll be thinking about the Grassmannian as being able to be written in terms of a matrix where, because it's a full rank K by N matrix, that you pick a set of K columns to be full rank. And I guess that would be important for the notation later because I'll be denoting that point as lambda, the point where you have the identity in columns lambda, and then you have zeros where the stars are. But if you just leave them as stars, then this will span an open affine set, which will be denoted use of lambda. Here, yeah, that's what I'm saying here. And use of lambda is isomorphic to C, K times n minus K, which is the dimension of the Grassmannian. All right, so let's talk about some combinatorics related to positroids before I give the definition of Positroid variety. So one way that I like to think about positroids is in terms of juggling patterns. So that's just a kind of simple basic example of a juggling pattern. So you think about time as moving to the right, and then each color is a different ball. So at second one, the red ball gets cut and it gets thrown into the air, and then it lands in the fourth second. And then, the second, a green ball gets caught and thrown, and this repeats every 6 seconds.
We're using only one hand?
Yes, exactly. A one-hand juggling pattern. So, yeah, there's more those aren't relevant in the case if there's like a two-hand model for positroids. So we can, take the set of numbers and then think about what sort of combinatorial data you can give to this. And I say, well, the most natural thing is to simply label what second the ball landed. So the ball from second one lands on the fourth second. The ball from second two lands on the 6th second. And so you could write it something like this. And this object is called, has a definition, it's called bounded affine permutation. So it's permutation from the integers to integers. You just add n to 6, 2n, 3n. Or you can go backwards, and so this gives you a permutation from integers to the integers that is periodic, period n. It also has this sort of bounded condition which says that you can't throw a ball more than 6 seconds. A ball that lands like 12 seconds later. All right.
Is there a version where you use two hands?
Okay, so I guess if it's even, if n is even, you could like just think of, I guess there's some cases in which you could just think of the seconds is
You
being.
don't want both, you don't want to have simultaneously balls on your hands at the same time.
It's just a permutation from 1 to n.
Yeah. But I mean, I'm saying, think about this as repeating, like this being periodic, so it repeats every n seconds.
But June, I don't think you have to catch those balls all in one hand. You just know how long they're in the air.
Okay.
And so maybe that I think you can see that as a pattern where you're using both hands.
So there's it.
Yeah. I mean, I guess you're just pointing out that, I don't know, you could technically, like there are juggling patterns where you have two hands and like they both end at the same time, but yeah, I'm not gonna comment on those sorts of juggling patterns. So here I'm just noting that there's another way that you can write. So the bounded affine permutation is before, it's the top line. You can come up with a permutation invariant set of numbers, or you just subtract 1, 2, 3, 4, 5, 6, and then 3, 4, 0, 3, 6, 2 would just repeat indefinitely down to the left or to the right. Here, I guess 1 goes to 4, so 6 would go to 9, etc. So it would, the bounded affine permutation would, it's a permutation from Z to Z, but the cyc swap is yeah, it's just the same numbers over and over again. Okay, so I say let's take this combinatorial object, cyc swap or just the permutation, and let's relate this to elements of Grassmannians. And I'm going to do that via this map called the bounded affine permutation map. And this is how I'm going to make it work. Is I'm going to say, let this be the first. Take a matrix that represents an element in the Grassmannian. Look at each of its columns, which I'm here denoting like I or J. And then for each column I, look at the first column to the right, where column I is in the span of all the columns to the right of I. So it's like I got rid of the example. Well, I'll just write a really good example. So for something like this, G of 1, so it's not going to be in the span of the second, it's not going to be in the span of the second column or the second, third, but it's in the span of the second and third. So tilde M is equal to, I guess here it's 4. So it goes to 1, 4, maybe a slightly more complicated example. Actually, I'm not going to do well, okay. What if I did this? Okay, so then GM2 would be 2, 3, 4, 5. That would be 5. Okay, so this sort of map that I've defined G tilde, this gives you, this is a different way to define a Positroid variety than what Daoji talked about last week. So these Positroid varieties, which I'm noting with this capital Pi, they're these subsets, varieties of the Grassmannian, defined by these cyclic rank conditions imposed by bounded affine permutations, basically for pi g. Think of every matrix that you can write giving an element of the Grassmannian k n, such that when you consider the bounded affine permutation corresponding to the matrix M, that it's less than or equal to G in Bruja order.
What do you mean bounded? I thought if these are periodic, I mean, does bounded mean that they're bounded over an interval? Like, what does actually bounded mean when you say bounded affine permutation?
Okay, so the bounded thing is the idea of the juggling pattern that when you throw a ball, it can't land more than n seconds later.
I see.
So it was f of I plus n is less or equal than f of I plus n. It's separate, right? It was
Yeah,
these lines ago.
yeah. I can return to that quickly, yeah.
Oh, I plus n, yeah.
So it's this condition that f of I is between I and I plus n.
The broad order is the same as the broad order for Sn.
Yes. Yeah,
Until the
or,
affine.
sure, I guess it's like it's circular,
But
but it's the same idea.
bounded affine transformation that correspond bijectively to elements of Sn, isn't it?
No, it's more.
Yeah, I guess there's,
And to represent every element. in
You have
the
loop,
N.
loop and code. You have loop and code. So you have a fixed point, you need a decoration. So the bounded,
This is like slightly larger than the affine Val group affine SN. Which is a semi-direct product of SN with translation. So this is slightly larger than that. I'm just,
Yeah, I don't see this.
okay, yeah, there's another definition, but it takes a little while, a little more work.
So this Brouwer order, is it in, the thing is as predictions, not in the Grassmannian.
Yes,
And also put it in like, you know, you have an element in a matrix corresponds to some element in the Grassmannian. And you can compare the cells. You can compare the
Yeah.
cells in which these elements.
yeah. Yeah, I guess another way you can think about it is just take the open Positroid variety of elements in the Grassmannian where it's the G tilde map gives you the exact same thing as the G defining your Positroid variety, then just take the closure of that. So there's a different diagrammatic way to depict the bounded affine permutation that will be useful at the very end, like basically the last part with the physics application. So basically you just G of 1 is 4. So you draw, I guess, 4 elements over, and then I guess G of 2 goes to 6. So the top line is given by the y-axis kind of moving down, and then the second, the permutation, is the horizontal axis. So you get a diagram like this. I don't want to say too much about this. Other than the fact that you can take the juggling pattern and then you can, if you draw lines to the right until you hit one of the ones and then move down, that you can sort of draw the juggling pattern on one of these diagrams. And then you can use this to define actually all cyclic ranks of your Positroid variety, and that gives you actually gives you a different definition of Positroid variety that might be a little bit cleaner or nicer to see than the one on Brouwer order.
Can I ask again?
Yeah.
I think we were trying to understand the difference between this bounded affine transformation permutations.
Yeah.
So can I make a jump of plus n?
Yes.
It's possible, and that's something that you couldn't capture with an element of Sn.
yes.
Yeah.
Then in Sn, the elements add up to and choose to. But I think they can add up to something else. Can just remove them.
Okay. Yeah, I think Daoji was mentioning that the fact that you can go 0 or you can go plus n, that enlarges the Brouwer order, like on Sn tilde from the one on, like the thing that you have for Sn is smaller. Yeah. Okay, so the proof is going to do something related to smoothness on Positroid varieties by using some kind of pipe dream. There's some sort of combinatorial diagram to make sense of smoothness. So the usual pipe dream story in SN, which is pretty classical or well-known story, is that a pipe dream is some diagram in a square where each box is filled by either elbows or crosses. And then you can think of the pipes as starting from the west and then ending on the north. And we call the pipe dream reduced if none of the pipes cross twice. So this would, okay, so this pipe dream corresponds to a permutation 1, 4, 2, 3. So these pipe dreams are not unique. In general, each permutation has multiple representatives, and the different representatives happen when you have this so-called cross elbow move. So when you have, I've highlighted in green and red, very appropriate for this season. When you have a cross between two pipes, and then you have this so-called near miss, you can switch the cross and the near miss, and you can get another pipe dream that gives you the same permutation. So I'm gonna skip this stuff about wiring diagrams. I mean, the idea is that you can think of these pipe dreams as being some sort of rotated wiring diagram, and then, well, maybe I should say that the wiring diagram gives you a way to write these permutations in terms of these transpositions. You know, some idea of you have some Coxeter group, and you have some letters that make up some word, and then yeah, some choice of word that gives you a permutation. So that's formalized in this paper by Knudsen and Miller. It's not important for what I'm doing. Oh, okay, yeah, I don't know. Okay, I'm just gonna move on to the sorts of pipe dreams that I'm working with in this research work, and that would be these so-called affine pipe dreams. They look like this as an example. So these are pipe dreams not for just permutations in SN, but permutations that are bounded affine permutations that correspond to a Positroid variety. So the outer shape is determined by your point lambda. I was noting earlier, I was drawing these matrices and noting how these points, they correspond to what patch on the Grassmannian that you're choosing to look at your Positroid variety on. So yeah, this is an example for this site swap or this bounded affine permutation. And you can form these by taking the columns, taking a matrix, and taking the columns 2, 5, and 7 corresponding to lambda, and then drawing what you call this red distinguished path, and then you eliminate the identity columns, and you take this distinguished path and you move it to the right, or you move it down infinitely, and you get this infinite strip. And that's the shape. As for what the elements inside how to get the crosses and the elbows, I'm just gonna briefly flip through the next few slides. So you can label the elements of kind of your word, thinking in terms of the rotated wiring diagram analogy, based off of the labeling of your distinguished path. And then there's some choice involved in how you read it. and then you take your bound affine permutation and you do moves until you get to your plus k permutation, and then that will pick out for you what the crosses are. Anyways, okay, so I'm going to talk about smoothness. I'm going to show you how you can use these diagrams to determine whether a Positroid variety is smooth at certain points. Smoothness is just the usual definition of smoothness. Okay, so the first thing is if you want to determine whether a Positroid variety is smooth or singular. So if you want to determine whether a Positroid variety is singular, it's sufficient to test it at one of the n choose k torus fixed points. So one of those points given by the lambdas, right? So yeah, so there's n choose k of them, and it has a singularity at one of those points, then it's then it's sufficient to know that it has a singularity somewhere. Like if it has a singularity somewhere on the Positroid variety, then it must be singular at one of these points. Okay, so the main theorem on smoothness is that a Positroid variety is smooth at point lambda if there's a single affine pipe dream representative for the affine permutation f on the open set U sub lambda. So if there's so the fact that this point lambda exists on the Positroid variety, so that's equivalent to there existing some pipe dream for the shape lambda. So the shape of the pipe dream corresponds to lambda, and if there's just one, so if there's no moves, then that Positroid variety is smooth at that point. So okay, a very, very easy example to display what this theorem is saying. So here there's no so this is the point lambda equals 1, 2, 3 corresponding to that patch on the Positroid variety in the Grassmannian, and this Positroid variety for this bounded affine permutation, there's no moves, so it's smooth. For this one, there is a move given by the blue and red pipes that have a cross and near miss. So you have these two different representatives, and so this is a singular point on the Positroid variety. Okay, so I'm gonna say something briefly about how to prove this result. I think the proof is very nice, so I'm gonna sketch it briefly.
There were also some results about projected Deletion varieties by Deletion and Schubert. That's right.
Yes.
Should apply as well.
Okay, yeah, so there is a way to, let me comment on that after I get the formulas on the next page. So the way that you go about this proof is you consider this multiplicity. And so it's a classical result that the multiplicity of a point on variety, so if that is 1, then you're smooth at that point. So we have to prove that the multiplicity of that point, lambda on a Positroid variety pi f, is equal to 1. And then in order to do that, we will make use of this theorem from Rossmann, and this is the case in which you have a variety that's a cone, and then if you have a dilation action on this vector space, then the multiplicity is equal to the coefficient of the equivariant cohomology. So the object that we're considering to use this theorem would be the class of this Positroid variety on U sub lambda on this open set. And there's these results by in this thesis by Michelle Snyder that Daoji mentioned last week, that gives a stratified isomorphism between these and this these Schubert varieties in the flag manifold. Okay, this is equal to this because this Schubert variety is contractible to a point, specifically the point v sub lambda, and then the last equality follows from the AGS Billy formula, and this is the formula that corresponds to the pipe dreams, the affine pipe dreams. So okay, maybe I should say, finish the argument. So if we restrict this to the C cross eigenvariant cohomology, then we can make use of the theorem that I just stated. And the coefficient, then it'll be a polynomial ring in one variable. The coefficient of that will be the multiplicity. So what we want to show then is that this formula, this AGS Billy formula, so that corresponds to the number of pipe dreams. So each affine pipe dream will give you add 1 times the variable, I guess I call it H, 1H. So if you have 3 pipe dreams, then it would be 3H, and that would give you a multiplicity of 3, which would imply that it's singular by the theorem that I stated above. All right, so this is the AGS Billy formula, gives you the restriction. This is really just a relabeling, rewriting of what we had above. So it's a statement across all reduced words within some big words. So Q corresponds to all the letters within an affine pipe dream, and then W would be some combination of crosses inside the affine pipe dream that give you the Positroid variety. So you can reduce this formula, this AGS Billy formula, to some polynomial in these variables y, and then by doing this restriction sets each term in the AGS Billy formula here equal to 1. So they'll literally just become a sum over all affine pipe dreams for that Positroid variety on that point. Okay, so now that we know how to look at a Positroid variety pi f on at a point lambda and determine if that point is smooth or singular, I'm going to give you a way to look at the pipe dream, affine pipe dream, and then determine very quickly and easily how whether it is in fact corresponding to a smooth or singular point. So here I say a pipe dream in rectangular shape reduces to northwest southeast partitions if it's a rectangular pipe dream where you just have partitions in the northwest and the southeast, and otherwise you have columns and rows of crosses. Okay, so actually to get back to Leonardo's, I just remembered your question. So there is a way alternative way to get this to write this as a projection from as a projected Richardson variety, which I can give you later. But it's the same thing. So it will also give you the multiplicity. You can look at that and use that to determine whether
So is this smooth if and only if the richest variety on top is smooth? More direction is clear.
Um, I'm not sure. I don't think so. Yeah.
So the AGS-Gilly formula that
Yeah.
you wrote down before, is that taking place in like the equivariant cohomology of the like Grassmannian or some affine version or like what?
Okay, yeah, so, yeah, good question. Yeah, so that is an affine, yeah. It is, I am really using some sort of affine AGS-Billy formula. Yeah, that they didn't formulate that in the affine case originally, but the proof goes through. Yeah, I can I have some notes if you're actually interested in why the proof.
I wrote a proof in the appendix of Billy's Duke paper that covers the cat's book.
Okay.
But
Well,
you're-
the point is
you're
this
applying
is
it to-
the open set around the point. It's an affine space. I think. I think that's what he. But affine as an affine space, not the affine Grassmannian. For the nature. Or maybe it works for both because
It
it's
is-
also, maybe it's both.
It is both.
Yeah. Because it's a rounded affine.
It really needs Michelle's result where you.
Okay, yeah, thanks, Daoji. So, okay, so this is yeah, an example of or northwest southeast partition. So I guess another notion is this notion of a maximal rectangle. Yeah, that's what, just as it sounds, you have a rectangle where the southwest and northeast edges touch the outer shape of the diagram. Okay, so this main theorem, characterization of a smooth point, says that if you have an affine pipe stream for pi f, restricted to use of lambda. So if every maximal rectangle reduces to northwest southeast partitions, then the Positroid variety is smooth at the point. So the proof is simply that you can determine whether there's a move on the affine pipe dream by looking at just these maximal rectangles. And then the way to check that each maximal rectangle doesn't have a move is to see that it reduces to northwest southeast partitions. So, okay, yeah, there are these two parts. So the first part is that every cross and near miss exists on a maximal rectangle. I guess the proof is not very difficult at all. And it follows simply from these shapes that each sort of yeah, since the pipe dream pipes only move northeast as you go up, they have to be contained in this sort of rectangular shape. And then the statement regarding these northwest southeast partitions, this is that's going to use this proposition, which is that a rectangular pipe dream is rigid if and only if elbow has no cross has an elbow both to its north as well as to its east, and no cross has an elbow to its south as well as to its west. So the leg condition, if you're familiar with Alexander Postnikov's work on Positroid varieties, the leg condition for these leg diagrams was was the southwest version. So, yeah, so no cross can have a elbow both to its west and to its south. So every pipe dream corresponding to a light diagram that he gave would be kind of this northeast pipe dream. Okay, so if you use that, then it's easy to see where this northwest southeast partition comes from. So every cross, since to satisfy both the northeast and the southwest conditions, every cross must be, since it has no elbow, every cross must have in this rectangular pipe dream must have crosses either to its north and to its east, and either to its west, to its and to its south. So that means every cross must be contained in one of these sorts of diagrams. And if you work out the details, then you have a northwest southeast partition. Okay, so the next part of my talk is going to talk about how we can put some sort of order on these objects, and the relationships between objects in this order will be this notion of deletion and contraction for Positroid varieties. So you should think of these deletions or contractions as being this fixed point set under this action, this sub circle contained within the torus, given by just one of the entries being not equal to 1. So this is just going to scale one of the columns. So the invariant things will be of one of these two types. Either you contain that column kind of by itself, or you don't contain that column at all. So we'll call this top version where you contain that coordinate, this contraction, and then if you don't contain that coordinate at all, then we'll call it this deletion. So deletion and contraction then become these Positroid subvarieties.
I tell you, my colleague, when I was just having my first baby, told me, "Oh, my wife is."
Okay, and then we can, I guess it's just notation, where you can define the contraction of the ith column of a Positroid variety is just being intersection with that Positroid variety. So in terms of the bounded affine permutation, what the deletion does is it comes up with the minimum number, the smallest number of these swaps, in order to put a 1 in the very left of the column. Okay, I guess on this diagram it's the row that you're deleting. All right, there's an algorithm. Contraction is by Grassmannian duality. It's just kind of the opposite diagram. So it's easy to see what then this deletion is when you restrict to one of these points. So I noted that each point or u sub lambda, this open set, affine set containing the point lambda, it's given by these pipe dreams. So the deletion for the pipe dream, it's kind of the minimal one that has, maybe it would have been clear if I had also labeled the top in the same way. So 1, 2, 3, 4, 5, 6, 7. That takes 4 to 4. So everything else here consists of elbows. I should have written out the bounded affine permutation, but so I guess then the question is, what if you take an arbitrary Positroid variety and you intersect with one of these deletions or contractions, which is how we're defining the deletion? Okay, so the answer is that you fill in the pipe frame with crosses along that column after you move the number, after you apply all moves to move the maximum number of crosses to that column. So pictorially, if I wanted to delete, if I want to intersect with pi del 3, I have to apply a move. I didn't draw the elbows and make it easier to see what's going on, but you would move this cross over here, and then you would fill in everything else in that column with crosses. And so that this would be this pi f intersected with pi del. So okay, so we can come up with an ordering where we have Positroid varieties, comma points. And the covering relation is if this this pair is obtained via this F1 lambda 1 pair via a deletion or a contraction. So I didn't include a picture here, but then this pi f lambda would, if you sort of drew out the partial order, it would have n lines going to things that it covers. So a neat proposition is that that this ordering interacts nicely with this property of being singular. So if you have a singular pair, sorry, I guess if you have a smooth pair and you go down in the order and you continue to be smooth. If you're singular and you go up, then you continue to be singular. So this proof, this was known. There's a geometric proof in this paper by Billy and Braden. You can give a really long combinatorial proof that I wrote down that's several pages long, involving how you move these crosses. Or you can give like a 2-sentence proof using the theorems that we just stated. And okay, so the theorem was that if you have a smooth point on a Positroid variety, then every maximal rectangle is in one of those northwest southeast partition things. So one of those things where you have some partition in the northwest and southeast, and otherwise you have, you know, columns or rows of crosses. So if you do deletion or contraction, you don't actually have any moves. So your deletion and contraction would just be adding columns or rows of crosses. And so it would maintain the form of a northwest or southeast partition in every maximal rectangle.
I have a quick question.
Yes.
Is the deletion and contraction that you're talking about here the same as deletion and contraction in the Positroid thought of as a positively oriented matroid?
Yes.
Okay, it's the same deletion and contraction, but
Okay. So yeah, if you look at what's going on the Positroid levels at the combinatorial level, it will just be this, you know, restriction and contraction thing that you're used to from the literature. Like the effect of intersecting with one of these deletion or contraction Positroid varieties is to, like, in the Positroid story, we have like matroids, you know, given by determinants, columns where whose determinants don't vanish. A deletion will just be like getting rid of that, the Positroids that have that column, etc. So okay, so an interesting question to ask is, what are the order ideal generators, quote unquote, or what are the minimal singular objects? So it's easy to see what these are in this story. Yeah, so any deletion or contraction of one of these, what I call atomic Positroid pairs, causes it to become smooth. All right, so they look like this. And this is just a statement that the fact that any deletion or contraction has to make it smooth means that you must have a cross that can move along the diagonal freely, and then everything else is is rigid, so none of the other classes can move. So, yeah, okay, so I'm gonna jump into some connections that I was thinking about in terms of physics. Okay, so we're thinking about trying to compute the amplitude. Okay, here's some details about S matrices that I'm gonna skip over. So in quantum theory, I know that we had the sort of joint physics combinatorics thing a few weeks ago. So it's probably a review. But in general, what we do in quantum field theory is we would have a Lagrangian, and the Lagrangian tells you how to draw these diagrams showing interactions of particles. And then the Feynman rules tell you how to take these diagrams and put down an algebraic or some kind of expression. And then you sum up a bunch of these up to some order, and that would give you this amplitude that you're interested in computing. So n equals 4, this usually is not described in terms of Lagrangian, but in terms of these particles, and you can write them in this nice way. So it turns out that n equals 4 super-Young-Mills theory is connected to these so-called plabic diagrams, these bicolored planar diagrams. They give you this. They give you these so-called leading singularities that you can use to get the amplitude. And usually the way that the calculation works is that you will, because you don't even really need the diagram, if you have a Positroid variety, then you write a matrix representative of the Positroid variety for C. So C is a matrix that gives you some open set of a Positroid variety. And then stick it into this formula, you'll get these leading singularities, or these on-shelf functions. One of the original ways to get a Positroid variety from one of these diagrams, these plabic diagrams, more specifically, you're getting the Positroid, or the bounded affine permutation, is that you move left. I guess some others have these switched, but you move left once you hit one of these white vertices, and then you move right when you hit one of these black vertices. And this will trace out for you a permutation, some sort of bounded affine permutation. So I guess the map really goes. So there's many different, this is not unique. You can do certain kinds of moves to get different plabic diagrams that give you the same bounded affine permutation. But so the map really goes from these diagrams to a bounded affine permutation, and therefore to a Positroid variety that the bounded affine permutation would label.
Is there some offshore version of what you wrote before? This was the onshore, right? So
Yeah,
it would be what?
So the offshore version would just be the traditional Feynman diagrams. Like this is the on-shell approach.
Some polynomials where you specialize and
So maybe,
no.
can I, the off-shell approach is generally very terrible. You get the same answer, but it's way more work. That's the short answer in this context.
Yeah. Yeah. I mean, yeah, these came from these sort of like maximal cut diagrams, which actually, yeah, Leonard, you were when I talked about leading singularities and tried to explain these maximal cuts, like that's where these diagrams come from. So the way that they originally, this paper by Nima Jake and Postnikov, Gottschalk, that they got that C matrix that I showed you in that formula earlier was by building up, by taking a Positroid variety, here I guess it's 4, 6, 5, 7, 8, 9, and then breaking it down via the so-called BCFW bridges, and then building them up. So you can actually do this from these affine pipe dreams. So you have to read in a specific order. So you read their BCFW diagram corresponds to reading from the southwest to the northeast. And all right, what are the BCFW bridges that you get? So you have to you follow this rule where you look at the vertical lines, so if it sort of comes in, then you have to increase the number of the, like this comes in, so the 1, 2 goes to a 1, 3. There's some additional details I don't have in these slides about what happens when you have a Positroid variety with crosses, but I guess here the example is if you somehow have this point, and you were considering the Positroid variety with all elbows, then you would get this sequence. This sequence would produce for you the BCFW bridge decomposition. And so this mathematically gives you a map from affine pipe dreams, certain types, because you have to use the so-called top pipe affine pipe dream, to plabic diagrams. Okay, so I have a few minutes left. I'm going to talk about inverse soft factors. So these inverse soft factors are a way where you can build up the differential form corresponding to the amplitude. The idea is that you attach, for these plabic diagrams, you attach these the set of 3 nodes. So there's a K preserving or a K decreasing inverse soft factor, and so that operation, using that operation, you can take these so-called maximally helicity violating or anti-maximal helicity violating amplitudes, which give you some differential form, and then you attach this factor, this combination of each d logs for a K preserving soft factor versus a K increasing soft factor. So if we look at what happens for the bounded affine permutation when you add one of these in, this is going to be the inverse. If you look at the diagonal diagrams, it's going to be sort of an inverse deletion or contraction. So it may be easier to see. So it's specifically, in most cases, going to be a 2-step for one of these diagonal diagrams. It's like a 2-step deletion or contraction. Is what happens when you remove one of these inverse soft factors. So doing an inverse soft factor, putting it in would be sticking in one of these things, and the details of what that does to a cyc swap. I mean, it's here, so it's not difficult. You put a 0 at the end. You make a couple of changes. Yeah, so I was thinking. I guess my talk is done, but I was gonna make a comment. So the putting in the inverse soft factors, that is not a commutative operation. So it depends on the order that you put it in. But deletion and contraction, that is just intersecting with these these sub-Grassmannians. So that is a commutative operation. So Thomas Line was talking about there's an idea of saying this factorization for amplitudes in terms of doing a deletion or as some sort of deletion across some sort of contraction. Yeah, something that I've been thinking about is whether you can use these inverse soft factors, use the commutativity of deletion and contraction for along the lines of these inverse soft factors to see some sort of deletion contraction structure for factorization. Yeah, if you have any ideas, please let me know. So. Just.
That was interesting, yes.